So welcome to the final exam review video for AP Chemistry Semester 1. In this video we'll be going over 3 units of study. The first will be bonding, then intermolecular forces, and then kinetics. These are the remaining units from the semester. The units that were previously covered were covered in another video. That was the midterm video, and that will be linked in the description below for everyone. So let's get into, we'll be starting with our bonding unit. So essentially, we'll just first start off with, and all of these sections are essentially just going to be broad overviews of the concepts, so that we can just so we're all just like reminded about the fundamental concepts, so that we are ready for those questions on the exam. Okay, so first to start off with, what are chemical bonds? So chemical bonds. So essentially what chemical bonds are essentially they're just mutual sharing of electrons. Let me zoom out here a little bit. So chemical bonds are just mutual sharing of electrons, and we know that these atoms are essentially bonded between the nucleus of one atom, and let's just say we have some electrons floating around here in a cloud. I'm just going to draw a bunch of electrons here around this nucleus. And then we have another atom here, and then we have another electron cloud around that. And essentially, these electrons of this atom are attracted with this nucleus of the other atom, and these electrons from the electron cloud of the other atom are attracted with the nucleus of the other atom involved in the bonding. So essentially, these here we can just call these our valence electrons, or VE, and so these valence electrons are attracted to the nuclei, and then that's essentially what creates our bonds. So now we'll go into the types of bonds, and first one I'll talk about is ionic bonding. Essentially in ionic bonding, there's again two atoms. So in one atom there'll be, let's say there's the nucleus, and then there's some valence electrons around here, something like that. And there's another atom, some valence electrons around here like that. So in ionic bonding, essentially one of these atoms is going to donate its valence electrons, or is essentially going to donate its valence electrons to the other atom to create a bond here. Or it can actually also go the other way around, where these valence electrons go over here. So in ionic bonding, there's going to be an electron donator and then an electron acceptor. If we take a pretty common ionic compound, let's say for example NaCl, essentially how this works is that an Na molecule is going to be donating, we'll just say that's an electron, it's going to be donating an electron to the Cl molecule, and this is what creates that ionic bond. And just something to note is that ionic bonds are formed between a metal and a nonmetal. And then the other type of bond that we'll cover is something called covalent bonding. So covalent bonds. And this is between two nonmetals. Essentially, how covalent bonding works is that let's say we have one atom over here and another atom over here, and then let's just draw an electron cloud here. Oops. Just draw an electron cloud here, the electron cloud here. Essentially, there's like a mutual sharing of electrons between these two atoms, and then this is what creates a covalent bond. So this is essentially the sharing of electrons here. Like I said before, these electrons here are going to just be attracted to that nucleus there, and then these electrons here will be attracted to that nucleus. And essentially what happens is in a covalent bond, what ends up happening is that these two electron clouds, they essentially want to repel each other. So right here there's some repulsion going on, and what this ends up doing is that it ends up increasing our potential energy, which is why if we end up just moving on from there, so just to cover, we have two types of bonds. One is going to be our covalent bonds, and the other is going to be our ionic bonds. Covalent bonds occur when there's like an equal sharing of electrons, like here, and then an ionic bond will be when there's a transfer of electrons from one atom to another, like in NaCl. So now moving on to another concept called bond energy. So bond energy. So this is essentially just, I'll just say E for energy. Energy that is involved in either forming or breaking a bond. And we want to keep in mind that forming bonds is a exothermic process. So therefore our delta E or delta H is going to be negative, and then breaking bonds, you have to put energy in to break bonds, therefore it's an endothermic process, so that'll be a positive delta H. And essentially stronger bonds will have higher bond energies. So bond energies are actually, so for the most part, bond energies, they're just like averages, and the average is essentially based on that's all you really need to know, is that the bond energies are just like averages, and that there's like essentially the bond energies are averages in that there is like values that are slightly higher and lower than that average, and it varies like a small amount depending on like sort of the environment that the bonding is taking place in. And then another thing to note is that bond energies is measured in kilojoules per mole. And then the next characteristic that we want to get into is something known as bond length. So essentially, bond length between two atoms is going to decrease our distance. So for bond length, how we measure it is when these two atoms are at their lowest potential energy. So I'll just say measured at lowest PE. And again, bond length, like bond energy, is also an average, and it's measured in picometers. So essentially 10 to the 12th picometers is 1 meter. And if we remember and we go back to previous units and something called Coulomb's law, basically according to Coulomb's law, which is basically just like charge and distance is the only thing you need to remember, charge and distance. Shorter, if the bond is shorter, then the bond will also be stronger because you have a smaller distance. If you remember, Coulomb's law is something like Q1, Q2 for the charges over R squared, something like that. The more the rate, the longer the radius, the smaller the I guess the level of attraction will be. So essentially, what we can say from that is that a shorter bond will be a stronger bond. And we can see that, let me just give some examples here. Let's say CN. If I just draw that bond here, it'll be something like this. It'll be a triple bond. The bond length for this is 116 picometers, and the bond energy is 891 kilojoules per mole. Now let me take another bond, which would, let me just take a CC bond with, it's a single bond here. We have a bond length of 154 picometers, and then we also have a bond energy of 347 kilojoules per mole. So you can see a very distinct pattern here in that we obviously have a triple bond here, so that results in a shorter bond length and also a greater bond energy, essentially meaning that the bond is stronger. Here we only have a single bond, our bond length is further, and then our bond energy is obviously less. So now moving on, we need to be able to determine the differences between ionic and covalent bonds. And essentially, there is an electronegativity scale that you can use, and that essentially it varies from book to book, but essentially it'll be 0.4, and you'll have 1.7, and then these values here, that value there is essentially just why isn't that going away? Sorry. So if I'm just gonna erase this real quick. So these values right here, 0.4 and 1.7, that's going to be our delta En, which is essentially just the electronegativity difference between the two atoms in the bond. So anything over here is going to be covalent bonds from anything that's less than 1.7. And then anything that's greater than 1.7 will be ionic. So some examples, NaCl, and then H2. So if we just look here, and for this you will have to know the electronegativity values. Just remember also on the periodic table, electronegativity, fluorine has the highest electronegativity with 4. And that electronegativity increases as you go up the periodic table, and from left to right it also increases. So keeping that in mind, if we just go ahead and we do the delta electronegativity, let's say for H2, right? Well, this bond is essentially just 2 H's. So whatever this is and whatever this is, it's just going to be x minus x, which is equal to 0. So essentially what we're saying is that this will have a delta En of 0, which then we can determine that this is a covalent bond that is also nonpolar. And then going into electronegativity, I'll just write En. It basically, electronegativity will apply in any compound where the atom is not alone. So electronegativity would not necessarily apply in the sense like of just like a single argon atom. It would apply in the sense of like a, let's just say argon could form, I don't know why this isn't working, but electronegativity would, so here, let me give a better example. Instead of argon, I'll say something like, I don't know, sodium. Electronegativity doesn't really apply to this single atom. Electronegativity more applies to when this atom is bonded with another, like in a compound such as NaCl. And what essentially electronegativity is, it measures how strongly the atoms are like attracted, how strongly the atoms attract electrons when it's in a compound. So a high En means that we'll just say atom wants electrons. But a lower En means that atom, I guess, doesn't want electrons as much. Doesn't want E minus as much. And like I was saying before, fluorine has the highest electronegativity of 4.0. And then basically all of the other elements in the periodic table were just determined by comparison with fluorine. And again, if I just try my best to draw a periodic table here, it'll look something like this or something. We want to remind ourselves that En increases when we go from the bottom of the periodic table to the top, and then En also increases from left to right. So essentially we can just say that the overall trend here is that electronegativity is increasing like this, like a diagonal across the periodic table for the most part. And then the next thing we want to get into is polarity. We talked about covalent bonds. We talked about covalent bonds. There's two types of covalent bonds. There's polar covalent and there's nonpolar covalent. Nonpolar covalent is basically when the electrons are shared evenly. So shared evenly, and I'll just write in parentheses E minus. When the electrons are shared evenly. So this essentially will result in a small, so we'll say small delta En. And then polar is when the electrons are essentially unevenly shared. So those are the two different types and then one thing I forgot to mention is that this will have a large delta En, because you have one electron that really wants you have one atom that really wants all the electrons, and then you have another that doesn't really want the electrons as much, and it'll just basically pull the electrons away. And then so now we can move on to some more bond energy stuff. Some things that we want to keep in mind is that like we said before, energy values are an average of the bond energies, because bond energy does change depending on the environment. And then we have a few different types of bonds, so I'll just say types of bonds. And we have single bonds, and then this is where one pair of electrons is shared. And then we have a double bond, two pairs, I'll just say two pairs shared, we're talking about electrons here. And then we have a triple bond, and then this is where three pairs of electrons, shared. And then the terminology known as if you ever see the word multiple bonds, that's really just referring to double and triple bonds. And then just a reminder, how this essentially works is that as we, I guess, go down this list, one thing that's going to happen is our bond length is going to go down. So I'll just say length goes down, but our bond energy is going to go up. And that's really just because there are more electrons being shared in the triple bond, meaning that we will need to use more energy to form or break a triple bond rather than a single or double bond. And then also because those electrons, there's a lot more of them, they're being attracted to the protons of the other atom, basically meaning that they'll be pulled in more, so that will result in like a tighter or shorter bond. So basically, so for bond energies, when it comes to calculations, we have delta H, which is just this is just the energy needed to break the bond. So energy to break bonds, break plus energy to form. And if we remember correctly, this is essentially energy to form bonds. When bonds are formed, this is an exothermic process, so this is actually going to be negative. But for simplicity's sake, I'll just say plus here, but that will end up turning into minus if we actually do this. And then energy to break, well, that's an endothermic process, so that would be plus. So that's essentially how we just like calculate delta H. And going back to this, delta H will be this will be positive if the energy to break the bonds is there's more energy that is needed to break the bonds of the reactants in the reaction than there is energy released from the products forming. And then it'll be delta H overall will be negative if the energy that is released from forming the products is more than the energy that it took to break the reactants bonds. Okay, and so we'll be now moving on to localized electron bonding model. So essentially this is just a model. It's not always true, but it's generally true. Just to summarize it, that basically for lone pairs, which we see those in like our Lewis dot structure, for lone pairs, these lone pairs will be localized on one atom, and it'll only be written around one symbol. And then for bonding pairs, we will have a we'll essentially just have there's just like two, there'll just be basically there's just like lines between the bonds. That's pretty much it. So this is like, it's not as important to know like the exact model. It just like basically is like, I guess, a pre thing for Lewis dot structures, which we'll get into. So if we remember correctly, Lewis dot structures just essentially showing how the valence electrons are arranged around the atoms in a molecular compound, and the goal is to essentially represent it so that the elements can fill their outer energy levels by sharing these electrons in covalent bonds. There's a couple things we want to remember. We have the octet rule, and essentially most compounds tend to form when each atom can gain 8 electrons in its highest energy level. So essentially it wants 8 valence electrons, because everything wants to be like the noble gases, which all have 8 electrons in its highest energy level. And then there's the duet rule, which really only applies to helium. And that's just like helium wants 2 instead of 8. So going into how to draw our Lewis dot structures. So I think it's best, because we're just reviewing this, I'll just go with an example. I'll say, let's draw the Lewis dot structure for CH3Cl. So we want to remember when we're drawing these dot structures that the central atom will always be the first one because it's usually written in order of electronegativity. So for example, in this compound, carbon is the most electronegative. So the most electronegative atom will be the central atom. So all I'm going to do here is I'm just going to add up the valence electrons. So if you take out your periodic table and you just go by the trends, we know that carbon will have 4 valence electrons, so that's 4 valence electrons plus, and then we have 3 hydrogens. Each hydrogen has 1 valence electron, obviously, so that's 3, and then each chlorine has 7 valence electrons, so that's 7. So in total we have 7 plus 7, that's 14 electrons. Let me just erase that. I don't know why the undo button isn't working, but 14 electrons. So essentially what I'm going to do to start off with is I'm going to draw my central atom, which is the C, and I'm going to just draw something like this. And what I like to do is I like to always keep track of how many electrons I've used. So in this case I have a single bond here, a single bond here, a single bond here, and a single bond here. All of those single bonds are going to take up 2. So I've used 2, 4, 6, 8. So I've used 8. Now I have 6 left. And we have to remember that hydrogen can only form 1 bond because it only has 1 valence electron that it can contribute to the single bond. So all of the lone atoms now, or all these 6 atoms, we can look here and we want to just we want to get to the octet rule for all of these. So all these hydrogens are satisfied. They can't do anything more because they've already contributed their 1 valence electron to this bond. Let's see, this carbon has a full octet because it has, again, 2, 4, 6, 8 electrons in its it has 8 valence electrons right now, so that's been satisfied by the octet rule. So now these 6 valence electrons are just going to be used as lone pairs around the chlorine. So I'll just draw 1, 2, 3, 4, 5, 6 dots around the chlorine, and then that is the Lewis dot structure for CH3Cl. So that was just a quick overview. Remember, to determine the valence electrons, it's really easy. You just go across the periodic table, and group 1, for example, has 1 valence electron, group 2 has 2 valence electrons, and so on. I guess we could do one more example. We'll just say NH3. So again, first thing I'm going to do, I'm going to add up the valence electrons. I know N has 5, and there's 1 N. So I'm going to just say this is going to be 5, and then plus H has 3 valence electrons, so I'm going to just put, H has 1 valence electrons, but there's 3 H's, so this is going to be 5 plus 3, which is equal to 8. And then I know that N is going to be central because it's written first, so I'm going to have N, then we have H, then H, then H. So essentially, I've now used 2, 4, 6. I've used 6 of these electrons, so now I have 2 left, and H can only form 1 bond here, so I'm just going to put this lone pair here onto the nitrogen, and then that's just a quick review of how we draw our Lewis dot structures. So moving on, I also want to say that there are exceptions to the octet rule. Anything that's in the third period of the periodic table and below can violate the octet rule, meaning it can hold more than 8 electrons, or more than 8 valence electrons at a time. So you can add lone pairs and multiple bond strip. For example, if I were to draw PCl5, P is in third period or lower, so I can have P, and then I can do Cl here, a Cl here, a Cl here, a Cl here, and a Cl here. And this is violating right here. This is technically violating the octet rule, but because phosphorus is lower than the third period, we're fine with violating that. So now moving on to drawing Lewis dot structures for polyatomics. Essentially how this works is that it's like any other Lewis dot structure, it's just there's a few adjustments. So let's say I take the polyatomic ion SO4 2-, and this actually goes for any ion they give you, and they ask you to draw the Lewis dot structure. I'm again just going to add up our valence electrons based off of the periodic table rule for valence electrons. So I know that S has 6, and then I know there's 4 O's. Each of those O's also have 6, so that's going to be plus 24. But then remember I have a 2- charge, so I actually have 2 more electrons. So then I know I'm going to have 32 valence electrons. So essentially I'm just going to draw out right here with my central atom being S. I'm going to just draw it out like this. So again, I've used 2, 4, 6, 8 of these valence electrons so far. So now I know I have 24 left. So now I can just use these 24. I can use 6 on each oxygen so that they all have satisfied their octet. So I can just go like this. I'll just go like that real quick. And then this is the Lewis structure, but when we're doing polyatomic ions, you have to make sure that you put these in brackets and then put the charge right here to distinguish that this Lewis structure is something that is an ion. So it's basically just a regular Lewis dot structure. You just need to make sure that you have that charge in the top right. Okay, so now moving on to resonance structures. So essentially resonance structures, what they're used for is when there are certain times when one Lewis structure is not a sufficient like representation of what the compound looks like. So not sufficient rep, I'll just say. So in this case, we need like multiple Lewis structures in order to show this. So let's just say I draw the Lewis structure of like ozone, so O3, and then I'll go down here and do this. So I'll say ozone. Okay, I know I have an O here, an O here, and an O here. If I just do this real quick based off memory, knowing what ozone looks like, it'll be something like this. And here's the thing about this structure is that, yeah, it's correct and everything, but this double bond could technically be over here as well. So that means we need, that means we have resonance, meaning that there can be more than one possible structure. So now I'll have an O here, and instead of drawing it on the right hand side, I'll draw it on the left hand side, the double bond. So I'll do a double bond here, and I'll go here, and then I'll have 2 lone pairs here, and then I'll do my single bond over here, and then I'll have 3 lone pairs here. And essentially what I'm going to do is I'm just going to draw an arrow like that in between that, indicating that these are resonance structures. So as we can see here, if we just recap that, we had a single bond and we had a double bond, but technically these could be switched. So in order to get a better representation of the actual Lewis structure, we drew 2. So on this one we had the single bond on the left hand side, we have it on the right hand side over here, and then we had the double bond on the right hand side, we had it on the left hand side over here. So that's essentially what resonance structures were, as just like a review. Now let's go into a little bit more of a complex example. Let's say we have the polyatomic ion NO3 minus. So to draw this, I'm first going to just do my normal routine of counting up the valence electrons. N has 5 valence electrons, so it's going to be 5 plus, and then each O has 6. There's 3 of them, so that's 18. And then I have the 1- charge, so I have an extra electron, so that's going to be plus 1. So I now have 24 valence electrons now. So if I just draw this real quick, I'm just going to go here, here, then here, then here. So at this point, let me just draw that last O right here. At this point, I've used 6 of my valence electrons, so now I have 18 left. So now what I'm going to do is, in order to satisfy I'm first going to start with satisfying the octet of the central atom. Right now it has 6. So basically I'm going to just add a double bond like right there so that it's satisfied. So now it has 8, so n is satisfied, the octet row is satisfied. So now I've just used 2 more, so I have 16 left. And now all I have to do is I will just draw these lone pairs here in order to satisfy the octets of the oxygens. And then this oxygen right here will have something like this. So if I just count this all up, I have 2, 4, 6. So I have how many lone pairs do I have? I have 1, 2, 3, 4, 5, 6, 7, 8. That's 16. 16 plus 2, 4. That's 20, and then 2, 4, like that. So now I can. So I remember I have to draw my brackets like this. Just pretend that's on the outside of the Lewis structure, and I'll just draw my charge here. But if we look here, well, technically, this double bond could be here or here. So therefore, we do have resonance here. So if I were to draw my resonance structures, I can just do this really quickly. I'll say, okay, I'll have my double bond here, and I'll go like this, like this. I'll have a single bond here, and then I'll have 3 lone pairs there, and I'll also have 3 lone pairs here. And then I'll draw my brackets with my minus. And then pretend I'm writing these side by side. I have to make sure I put my arrows in between it to show that it's resonance. So I've done the double bond on the top and the right hand side, so now I'll do it on the left hand side. So I'll have an O here, and then I'll have an N, and I'll have a single bond here and a single bond here, and I'll draw my brackets. Let me just zoom out a little bit here. I'll draw my brackets. I have a -1 charge, and then all there's left to do is just draw or put in my lone pairs here. So I'll just have this and this and then that. So a little messy, but that's essentially what it would look like if we had resonance with a polyatomic ion. Remember that I'm putting these arrows in between the structures to show that they're resonance. And then I'm also showing that there's a charge on this ion right here. So moving on to now a concept known as formal charge, which we should all be familiar with. Formal charge. To abbreviate, we could say FC. Essentially, formal charge just like helps us compare various like different Lewis structures, and it helps us like determine which structure is like most likely to be the actual Lewis structure of that compound. So the formal charge is like not really a real thing. It's more like bookkeeping to see like how well our Lewis structure is actually, how close it is to the actual compound. So we could say that FC for something would be the number of valence electrons it's assigned by the periodic table, and then minus the actual number of electrons that are assigned to it. And so it's, so like I said, it's more like oxidation numbers rather than like an actual like charge or anything. And the goal of this is that I'll just say goal is that FC is equal to 0. And then just to make sure you're doing this right, one rule we want to keep in mind is that a negative FC, a negative formal charge, has to be in the most electronegative atom in your Lewis structure. So just to make sure you're using this properly, that's something you should keep in mind. So let's just look at an example. Let's say I can draw SO4 2 minus. I can draw it in multiple ways. I can draw it like this. I can draw it like this. Let me just draw this Lewis structure real quick. Let me just finish this. Okay, there's one Lewis structure I can do. So determining formal charge, I can look here and I can say, okay, well, if I was just to look at the FC of this oxygen over here, if I go back to my formal charge like sort of formula, I can see, okay, number of valence electrons assigned by the periodic table. Okay, I know oxygen has 7. And I know that here, well, I have 3 lone pairs and then a bond, a single bond. So I know I have 8 electrons assigned to it. So therefore, formal charge is -1. So if I go here, the formal charge for all of these is going to be -1. And then for the sulfur atom has 8. So in reality, it would have 10 valence electrons according to the periodic table. But here we have 8 valence electrons assigned to it because we have 4 single bonds. So therefore, it has a formal charge of +2. So we'll say +2 here. So, and then, for example, let's say I want to draw this Lewis structure a different way. Let's say I want to draw S here, and then I want to use double bond here, double bond there, and then I'll do single bonds here, single bond on the top and bottom of this Lewis structure. And let's just say I have 2 lone pairs here, 2 lone pairs here, 2 lone pairs here, and then I have 3 lone pairs on the top and bottom. So I know if I'm going to determine formal charge, I have, so for oxygen will have 7 valence electrons, and then I know that here, at least I have 1, I have 2, and I have 4. So I know I have 8. So if I do 8, that's going to just be -1. It's going to be -1. This is going to be -1. And then this is going to be 0. Formal charge is 0. Formal charge is 0. And then this is also going to be -1 here. So based on this, if we just look at the overall formal charge for this, we have +2 and then -4. So -2 overall formal charge here. And then here we have 0, 0, and then we have -2. So overall formal charge here is also -2, but we have more like atoms here that are close to a formal charge of 0 than we do up here. So we therefore know that this is actually going to be the atom that is more like close to the actual Lewis structure. So yeah, basically you just want to write out, and if they give you they'll probably give you multiple Lewis structures, just make sure that you refer to this formula over here for formal charge, that the number of valence electrons minus the number of electrons that are actually assigned to the atom, that will give you a formal charge. So moving on, we'll talk about bond order. And bond order is pretty simple. So a single covalent bond, that's a bond order of 1. And then double, and then double covalent, I'll just draw an arrow, that's 2. Then triple covalent, draw an arrow down there, that means triple covalent, that'll be 3. And then for our resonance structures, it's really just like an average. So for resonance, it can be like something like, depending on like what we have, it could be like, let's say that we have like one that's triple and then one that's double. Well, then it's going to be 2.5. So we can have like 3/2 order. Like we can have, let's say 4/3. Anything like that. It can be a fraction as well. That's for resonance. So if you have resonance, you're just going to average the bond orders, and then that will give you your overall bond order between all those resonance structures. So the next thing we can move on to is Vesper theory, which is essentially just like electron and molecular geometry. So what the Vesper theory basically states is that there's going to be repulsion between the electrons that are around the atom. So if I have like an atom here and I have like this whole electron cloud around it, something like this, these electrons here, they're going to be repelling each other. There's going to be repulsion. So essentially what that does is that it pushes these electrons want to be as far apart as they can be, so as far apart as possible. So knowing that, what we can do is we can then use that and predict the shape of the molecules or the geometry. I'll just say predict geo. We're predicting the geometry. So basically for geometry we have a couple different shapes, and we can basically so for electron we have electron geometry, which simply just looks at the number of electron domains, which can also be called the steric or coordination number. I just like to say electron domains. So for example, if I were to draw like a Lewis dot structure of something, and I were to say, okay, I have an atom here, or here, let me just do this. I'll just say there's an atom here, and then there's a single bond here and a single bond here. And so this would have two electron domains, because a single bond counts as one electron domain. So I have two electron domains here. So then this would have a shape of linear. And then if I just keep going down the line, 3 electron domains, so I have something like this. Just pretend these circles are like our various like atoms that are involved in this Lewis structure. So I'd have 3 electron domains. So then this would be trigonal planar. And then moving on, let's say I had 4, so I'd have something like this. I can see I have 4 bonds here, so that's 4 electron domains, so that's going to be tetrahedral. And then I think you're probably getting the idea now. If I draw something with like 5, do something like this. With 5, that's going to be a trigonal bipyramidal. And essentially, then the last one is going to be 6 electron domains. That's going to be 6 bonds. So if I just go here and I go 1, 2, 3, I go 1, 2, 3. That's going to be octahedral. So this is electron geometry, which is essentially just based off of a number of the electron domains here. So essentially all I would say for this is that you're just going to want to draw out the Lewis structure and then determine the electron domains from there. There are like exceptions to this for molecular geometry, which is a little different. Like for example, let's say that we have like something, let's say that we have, what if I do something like SF4? Well, S is going to be the central atom. I'm going to have F here, and I'm going to have F here, and F here. So there's going to be a lone pair right there. And essentially, this shape is going to be different because what this lone pair is that these electrons here are going to repel these electrons here away, which is going to change the shape. So so if this was electron geometry, well, I have 5 electron domains because each lone pair counts as one domain. So I'd have 4 single bonds and then that one lone pair, which is an electron domain. So technically, if I'm talking about just electron geometry, this would actually be a trigonal bipyramidal. I'll just say trigonal bipyramid. But because I'm talking about molecular geometry, there's all sorts of different shapes that can form based off of this sort of like distortion of, I wouldn't say distortion, but just because these lone pairs are repelling the electrons involved in the bonds, it's going to change the shape. So if we're just talking about molecular geometry, this is going to be called something called seesaw. And honestly, I would just like really go and try your best to memorize these if you don't know them already. Electron geometry is really easy, but for molecular geometry, you're really just going to want to memorize the shapes. And then if we go into hybridization, so for this, hybridization is basically just the crossing of like orbitals. So we know the s orbital is like a sphere, and then we know our p orbital looks something like a dumbbell. So let me try drawing this as best as I can. That kind of looks like a dumbbell. So we have our p orbital here. If we just add these, this is going to create like a hybrid essentially. So I'm going to have like, here, let me erase that. That's kind of a bad drawing. I'll just erase that real quick. I'm going to have something like this, and it'll look something like that. So that actually looks, it's hard to draw in here, but it looks really similar to the other one, but it'll be something more like this. So it's going to be like a hybrid between these s and p orbitals. The only thing that you really need to know is that if we have, let's say that there is, let me think, let's say that there's like two electron domains, so 2e minus, 2 electron domains, that's going to be sp hybridization. And then if I say 3e minus, and then just pretend I'm writing domains here, that's going to be sp2. 4 will be, if I'm remembering correctly, 4 should be sp3. Yeah, sp3. 4, sp3. And then 5 will be, that will be sp3d hybridization. Then 6 will be sp3d2 hybridization. So essentially, this is all you really need to know for hybridization, is just based off of the electron domains, what is going to be our hybridization. So I just memorized those. And then sigma and pi bonds. So sigma bonds, I'll try my best to draw this. The symbol looks something like this. Sigma bonds, it's the region between two bonded atoms. So I'll just say between two bonded atoms. And then pi bonds, obviously we all know the symbol pi. This is going to be above and below the line that is drawn, line that bonds, that the line that's between the two atoms that are being bonded. Again, for the most part, you're really just going to need to know that for single bonds, I'll just say single bonds, we have one sigma bond, so I'll just say one sigma. Double, we have one of each, so I'll say one sigma, and then I'll do like one pi. And then for our triple bonds, I'll say one sigma and 2 pi. So just remember that, because there will be questions just asking you, hey, in this bond, how many sigma and pi bonds are there? That's really all that you are going to want to know for that. So, okay, the next thing that we're going to want to look at is polarity. We mentioned this before, but polarity is just like, we can classify it into nonpolar and polar. Like we were saying before, there's nonpolar and polar covalent bonds. Polarity, essentially it's like, when we talk about it, we usually say like there's like a like a net partial or negative charge on a molecule because of the uneven distribution of charge. So if I were to give an example, I could do something like, let me just think real quick. Let's say I have HCl, and then I have, let's say I have H here and I have Cl here. Well, if I should draw like, so Cl has a higher En, so it's a higher En. So it's going to pull all of the electrons this way. So therefore there's going to be something called a dipole moment, net dipole moment towards the Cl, because it has a higher electronegativity. Similarly, if I just draw something like, let's say I draw something like SO3, well, I know that S is going to be my central atom and that these O's all have higher electronegativity than the S. So therefore, there's going to be dipole moments here, here, and here. And this is essentially just the O's pulling the electrons more than the S. That creates that uneven sharing of electrons. So that was just a quick review of polarity and dipole moments. And the next thing I would probably want to go over is lattice energy. So lattice energy is essentially just like, so if we look at a lattice energy, so this is just energy to separate like gas ions and then form them into an ionic solid. So let's say that I have like ion Y, and that has a plus charge, plus ion X, and these are in both the gas stage. X has a minus charge and they're both in the gas stage. That's going to go to My, or oops, sorry, why am I saying M? I'll say YX, and then I'll say this is a solid. This process of going from a gas to a solid is going to be a exothermic process, meaning that energy is going to be released. So therefore the delta H for this reaction is going to be negative because energy is being released. Let's say I do the same thing, but these are now in the solid phase, so I'll do Y minus solid plus X plus solid, and that goes to YX in the gas state. If you think about it, like let's say I have like an ice cube. I have an ice cube here, and then I want to take this water and I'm gonna like melt it. Essentially, I'm gonna just like melt it into a puddle, and I'm gonna have to add even more heat to like make those water molecules turn into steam. So the delta H for this is going to be positive because we need to add energy for this lattice to essentially break apart and then form into gas ions. So when the lattice is formed, it's an exothermic process, and when the lattice is broken, it's an endothermic process. Essentially for lattice energy, it happens in a few steps. The first step is going to be the sublimation of the solid. I'll just say delta H sub. Step number 2 is going to be the ionization of the gaseous metal ions, which is going to be essentially just the first ionization energy. So I'll just say ionization of gaseous whatever metal atoms. And then the third step is going to be the dissociation of the non-metal molecules, which is essentially just going to be the bond energy. So I'll just say dissociation. And if you just add up like all of these, what you're going to get is just going to be essentially this will just essentially be the formation of an ionic solid right here. So I'd say like overall delta H for this. All you need to know is that you're just gonna add up the ionization energy, the energy to sublimate, and then the energy. Oh, sorry. There's two more steps. I completely forgot. So there's also step 4 and 5. So 4 is the formation of the nonmetal ion, which is usually an exothermic process. So you dissociate the nonmetals from the metal, and then you're gonna form those, and then you're gonna have the formation of the solid. So formation of solid. Essentially, this is going from gas to solid here. So formation of gas ions. Also generally exothermic. Because at the end of the day, we're forming bonds. So all I would say for that is just to be aware of the coefficients in your chemical equation, and make sure you're using the proper stoichiometry. And if you just add up all those steps, essentially, then you should get the overall delta H for that. So that will conclude Unit 5, which was all about bonding.